Now that you have a good understanding of the basics of differentiation, we can move on to look at two closely related and very important aspects of integration. The first is antidifferentiation. So you've learnt differentiation, we want to be able to go back the other way. We call that antidifferentiation. And a very important part of integral calculus is finding the area under a curve. These two things might not seem related at all, but in the amazing fundamental theorem of calculus, we'll see that these come together. They're very closely related. So in effect, it's this fundamental theorem that links integration with differentiation, because antidifferentiation and differentiation are obviously very closely linked, and then the fundamental theorem joins these two for us. So, first of all, finding the area under a curve. Well, that's no problem from our just standard rectangle understanding of area, length times breadth. We can have a curve here, and we want to find the area under it. We can just divide it up into a number of rectangles, find their area, and add them all up. Of course, this example here is not going to be fantastically accurate because the rectangles are so wide. We can easily solve that. We make the rectangles thinner and thinner until, you guessed it with calculus, we form the limit as they get smaller and smaller. So the limit of lots of rectangles that are tiny, tiny, hardly wide at all, find their area, add them all up, and that's the calculus approach to finding the area under a curve. How do we do this? The area will just be the width, which we'll call in the limit, make it very small, delta x, and in the limit as delta x goes to 0, we'll just call it dx. We're used to d dx from dy, dx. That's what the dx is symbolizing, the limit of delta x getting smaller and smaller. So these areas here will be dx, this tiny width, times, well, how high do they go? They go up to the curve, which is f of x. So it's going to be a lot of products of f of x times d of x. That's the rectangle area, and just adding those up. So let's see the notation we're going to be using. The area under the curve, this pink thing, which we can label big A for area, this is going to be, now don't get thrown by this symbol yet, just think of that as saying add up the sum of all the rectangles, all the fx times dx, the height times the width. And that's all we're saying here. But now, because we're talking calculus, we're talking limits, instead of using the normal summation sign, we use this extended s, this sort of stretched s sign, the integral sign, but it still means the same thing. Just add them all up. And here it is the sign for integration. So there's an important exercise for you to do here with GeoGebra that I hope you will make the most of, so that you can really understand this limit idea being applied to areas now, just as we applied limits to gradients back in differentiation days. Then we come to antidifferentiation, and that's not so unusual for you. Antidifferentiation means going back the other way from differentiating, just like square root is the going back the other way from squaring. And again, some notation before we go much further. We are used to writing f dashed of x for the derivative. For the antiderivative, for now, we will use the sign big F of x. So we've got our function little f of x, as we're used to using that function notation now. The derivative we can write as f dashed of x, and the antiderivative we can write as big F of x. We won't use that symbol so much once we get into actually using the integration symbol, but for now that's a very useful way to describe the antiderivative, or to write it. Well, what is the antiderivative? What are we talking about? Let's say we had an fx of 3x squared. Okay, well, we can find f dashed of x very easily. Differentiate 3x squared, we'll get 6x, no problem. How about going the other way? Get big F of x, find the antiderivative. That means, what would we have had to differentiate to get back to 3x squared? Well, what do we differentiate to get 3x squared? We differentiate x cubed. So we say that if little f of x is 3x squared, big F of x, the antiderivative, is x cubed, because if we differentiate this thing, we get f of x, 3x squared. If we differentiate x cubed, we get 3x squared. So big F of x is x cubed. But here's a teaser for you now. Suppose we had little f of x is 3x squared. How about if I said to you, well, I think big F of x, the antiderivative, is actually x cubed plus 4. How do we handle that? Let's differentiate this big F of x I think I've got and see if it does give little f of x. If I differentiate x cubed plus 4, what do I get? 3x squared plus 0, which is our original little f of x, just ordinary 3x squared. So in general, we can actually write big F of x equals x cubed plus c. C is some constant, some real number. So there's an infinite number of possible antiderivatives to any given function. And because there's no unique solution, we talk about finding the indefinite integral. So if fx is 3x squared, the indefinite integral big F of x is x cubed plus some constant, and that constant can take any value. Does this make sense though? I mean, how can we have a function with an infinite number of antiderivatives? Well, let's think about it a bit. What do you know from your transformation work? How does the graph of y equals x cubed plus 3, or x cubed plus 4, or x cubed plus anything, how does that compare with the graph of x cubed? Well, it's just moved the thing up or down a bit, moved the curve up or down the y-axis. What's happened to the gradients? They're the same. Just moving up or down the axis, y-axis, does not change the gradients. And so calculus and geometry agree. That's very nice. So with this understanding now of area under a curve and antidifferentiation, we're ready to link these with the fundamental theorem of calculus. A marvellous theorem, a very powerful theorem. And here it is, the fundamental theorem of calculus. This summation, this integration of all the little rectangles that were dx wide, this fx times dx, the area of these little rectangles, added all up, is just the antiderivative of the function f of x evaluated at b, minus the same antiderivative evaluated at a. So this is linking area, because this is what we know is the area under the curve between x equals a and x equals b. And this is the antiderivative. We evaluated at b and then at a. Wow, this is powerful stuff and opens up so many possibilities in maths for us. Okay, but a question. we've just seen, looking at the antiderivative, how in fact there's an infinite number of antiderivatives for any given function. How can we handle that with integration, with finding the area under the curve? Well, no problem. It's the subtraction here handles that for us. Because if our antiderivative of fx has a constant in it, then that constant will be here when we evaluate the antiderivative at b. It will also be the same constant here when we evaluate the antiderivative at a. So we subtract here from here, that constant just disappears. So it's not a problem. And that's very nice because we don't want to be getting an infinite number of areas for one area under one curve. But we don't. It all works nicely for us. Okay, well, that's enough basic background for you now. It's time for you to do some work with finding areas under a curve, doing some work with the fundamental theorem of calculus, and then once you've got hold of that, we'll be ready to go on and look at finding volumes of rotation around the x-axis and doing many different applications.